Correct. So I want to talk to you guys about something called the Hall effect. And the Hall effect is an application of what charges, how charges behave in a magnetic field. So I guess we need to just recap that. When you have a charge that's moving in a magnetic field, what happens to that charge? It feels a force. Don't be afraid to say it. It feels a force. Um, And so we're going to use that to our advantage because we know about this thing. And we're going to come up, and Paul, the person who came up with this, is going to come up with a very neat application for it. Okay, so here you have a circuit. And I'm going to call this, make it draw like that. Good morning. So here I have a voltage source powering a current. All right, and this current is like starting from the plus here, going around, coming through this way. Let me draw it the other way around because I just realized the magnetic field is pointed upwards. It's going to be a net plus on this side and a negative on this side. So the charge is going to go around this way. It's going to enter here. And then once it enters, there's this big blue plate. And this blue plate is, what you need to know about it is that it's just conductive. All right, there's nothing special about it. It's just like iron plate. That's as much as information you need to know about this. And what's going to happen is when it reaches this point, when the current reaches the point where it touches the plate, it's still going to do what it naturally wants to do. And what it naturally wants to do is go to the area of lower potential. So here's going to be a high voltage, and here's going to be a low voltage, right? So the current is still going to dot, 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 go in that direction and leave the plate and then do its circuit. Okay? So why the heck do we care? Well, I haven't done anything to it yet. That's what the current would do if there was no external magnetic field. Now imagine I applied a magnetic field in the upward direction. Okay? And so now I have charges that are entering this plate. Okay? And there's a magnetic field, and so therefore it feels a force. So we need to use our right hand to know which way the force is going. So we have a charge going in that direction with a magnetic field upwards. So therefore there's going to be a force in this direction. Okay? There's going to be a force in this direction, a magnetic force. Right? But it's still going to want to go towards the area of low potential. So now what the charge does in the presence of a magnetic field is this. Okay? So it's still going to get attracted by that, right? And as it gets closer to it, it's going to get a higher and higher attraction. Except that before it gets to that side, it's going to kind of like arc outwards towards this end of the plate. All right. Now again, why does that matter? The answer to that is, good morning. The answer to that is, well, if I've made a local high concentration of charge here, right? And that's high concentration of electrostatic forces compared to the left, which is a low concentration of electrostatic forces. Then what I've just created is another voltage drop, another voltage difference. All right. So now there is a V high here and a V low here. One end of my plate is going to have a low voltage, and the other end of the plate is going to have a high voltage. And that's great because now I can connect wires here and here and have a totally separate circuit powering something else. Like that. Okay, a totally separate circuit. All right, so imagine that this here, this current, is totally separate from this one here. All right? And I've only done that because I've applied a magnetic field in my plate here. All right? And, well, again, what's the application of this and why do you care? Think of how many things get activated by magnets, right? So let's say you have, you guys enter through the front door down there. You use the magnetic strip to swipe your card and it opens the door. Well, that magnet in your card, it's not really a strong magnet, but it's still a magnet nonetheless, is actually providing a Hall effect to one part of a circuit. It's creating another circuit, and therefore you're sending a current in a new load. All right, so let me just recap that for you guys. When there is no magnetic field, the current goes like this and comes back. Okay? There is no current that goes laterally in this plate and does nothing for this. There's nothing for this resistor when there's no magnetic field. Introduce a magnetic field. What's causing this magnetic field? A magnet. All right. So you introduce a magnetic field, and now all of a sudden the electrons or the protons or however you want to look at it, in reality it's electrons. The charges are going to go do this, creating a voltage difference between the two ends of the plate, and the voltage difference is used to power a separate circuit, right? And that separate circuit is only activated when in the presence of a magnetic field. That makes sense? Yeah. Yeah, well, every circuit's going to have a load, something that it does. So I just drew a resistor. Yeah. Yeah, the squiggly line at the top? Yeah, that's a resistor. Yeah. Oh, I drew it in the wrong direction. This direction. Thank you. All right. So here we see the same effect. So I have my current coming here, my usual current coming here with a magnetic field pointing upwards. And when there's a magnetic field and a current going this way, some charges are going to loop across the plate this way, and then create a voltage difference between this, which we call V Hall. V Hall is the voltage difference of the Hall effect, right? And then you use that to measure or to power whatever other circuit. So again, if there is any of you guys who want to do this for your project, also a great idea. Yeah, that's right. Yeah, yeah. Explain that again using this diagram. So V Hall, from what I explained on this one, would be the voltage difference between this and this. Yeah. Okay. There isn't too much more about it. These are just all different ways of explaining the same thing. I'm never going to ask you guys to calculate this because this we've already learned before, and we're actually going to learn a bit more about it today. All you need to know is the concept of the Hall effect. Okay? So you can cross this little equation out at the top here, and there's some problems for you guys to practice with. So we can do this one real quick. No, actually, this is something else. We're going to come back to this after I speak with after I talk about the second part of the of today's lesson. You need something else to be able to do this. That's it. Okay, that's the Hall effect. Let's go to PowerPoint number 27. Ooh, I wonder if my video works here. Okay, so induction is this unit's name. Induction is going to be something of kind of a complex topic, and is also going to be the last major topic that we're going to do in this course. There are two other kind of like subtopics, but they both have to do with inductors, and it has to do with induction. So I grouped them all into one kind of unit, and it's not that hard. It's just sometimes it can get a little mathy, and that's it always makes some mass confusion. I don't know if you remember, but I had this symbol when I was teaching you guys Gauss's law. So I would compare this to the difficulty of Gauss's law. In order to understand this, we have some new laws to follow. There's Faraday's law and Lenz's law, and they are together what induction is about. All right, so Faraday's law will explain the concept behind it. Lenz's law will explain the direction behind it, and then together they form the idea of induction. So there are two kinds of things that we're going to look at. I'll go through both examples. But essentially what we need to understand here is magnetic flux. You guys remember about electric flux? Yeah, okay. What was electric flux again? What were the things? Yeah. Exactly. So what do you think magnetic flux is? Same thing, but instead of electric field, it's magnetic field, okay? So it's the amount of magnetic field that goes into an area. And can you guys remind me, if I wanted to maximize the flux, what did my spatial orientation need to be between my electric field and my area? It was what? What did it have to do between my electric field and my area? Yeah, how much? 90 degrees, exactly, right? So if my electric field and my area were perpendicular to each other, then I would maximize. And if they were parallel, what would happen? It would be zero, exactly. There'd be no flux. All those concepts, you can reapply them here. Just replace everything that's an electric field, replace that by magnetic field. And now instead of having electric flux, we're having magnetic flux. The symbols even are the same thing. So it's really not all that different. We're going to learn about something called motional EMF, and you'll see it's not, it's kind of what we're talking about here. It's all about flux. We'll get into it. I don't want to get into too much about motional EMF just yet, but if there is one very important sentence in this slide is this, all right? And this is Faraday's law, plain and simple, all right? Think about flux, the magnetic field entering an area. The change of flux is going to generate an EMF. And an EMF, I'm going to define it now as an electromotive force. My God, twice in one word, electromotive force. All right, and an electromotive force is actually just a voltage. Basically, what we're going to do is we're going to change the magnetic flux. When there's a change of magnetic flux, there's going to be an induced voltage, right? And that's why it's going to be called, this whole unit called induction, because all we're doing is we're moving around magnets and we're inducing current in something that has normally no potential difference. Okay? So please remember this word change. Right? If I say change, what mathematical tool does that make? Which one? Subtraction? Yes, if you're talking delta final minus, or sorry, delta is equal to final minus initial, that's subtraction. But if we're talking about it more in terms of like very fine, infinitely small changes, we're talking about which mathematical tool? Derivatives, exactly, yeah. All right. Sorry, the heater's going to do that. So let's talk about how all this applies together. Okay, so first we need to understand magnetic flux because it's the change of magnetic flux that induces an EMF. All right, so let's figure out the change, or let's just figure out the magnetic flux. The symbol, if you remember, for flux from when we did Gauss's law was phi, and it's still phi. And this time, except it's phi sub b for magnetic flux. And it's equal to the dot product of these two vectors, the magnetic field vector and the area vector. And when I have a dot product, sorry, Elizabeth, when I have a dot product, how could I measure the magnitude? If I have two vectors and I'm trying to find the dot product, if I want to find the magnitude of that dot product, how do I manipulate my two vectors in order to get that magnitude? What's that? It's going to be equal to 0? No, not quite. Only going to be equal to 0 if they're parallel. Yeah. Exactly, yeah. So it's b times a, or the magnitude of b times the magnitude of a, cosine of the angle between them. So you guys said and the magnetic perpendicular, but is that actually the case? What is cosine of 90? Cosine of 90 is 0. And so how does that work into it? Because we just said that it had to be 90 degrees, but you tell me now that 90 degrees is 0. So what are we missing here? Yeah. It's the normal of the area, exactly. So if you guys remember, I'm going to change colors here because it's going to not appear very nice. If you remember that a surface like this has an area vector in which direction? Yeah, it's going to have it in that direction, perpendicular to the surface of the area, right? So in fact, the area vector and the magnetic field vector, they have to be parallel if you want them to be maximum. So the A vector, so the A vector and B vector should be parallel. Okay. If we take a look at the equation, just first off, what we see is that it's magnetic field multiplied by area. So the units of flux, you can consider them to be as Tesla times meter squared. But we have a special unit for it called Weber, and that's equal to Tesla times meter squared, the same thing. Those are the units for magnetic flux. I mean, just so you know, Weber's is WB, not just W. W is which unit? Watts, exactly. Okay, so that's what flux is, right? And we have to remember that when we're dealing with this topic of induction, it's not just flux that we need to know, it's actually the change of flux. So we're going to come back to that in a second. Here's a little reminder on how magnetic flux is similar to electric flux. You know, it's very, very, very similar. And I'm just going to, can I write on the side here? No, I can't. Okay. So I'm actually going to go back to write it here because there's more room for me to write it. Do you guys remember that flux is equal to the surface integral of the magnetic field multiplied by the area? Whether it was the magnetic field or the electric field, doesn't matter, it's the same equation, but it was a surface integral of that. And what we simplified it as is if we have a uniform magnetic field or a uniform electric field, we can take that out of the integral. So if it's a uniform magnetic field, we can take that out of the integral. If it's not a uniform magnetic field, then we can't do any of this fancy math. So what we can say is that it's B surface integral of dA. And the surface integral of dA, well, that's easy, that's just A. Right? But this only works only if always, sorry, only if always, oh, I mean, my grammar is going to be a bit bad here. Let me just rephrase this. So this only works if B and A are parallel. So it's easy to find it at one spot, but if I'm talking about a whole surface and an entire magnetic field, then what you need to do is one, make sure that your magnetic field is uniform, right? And two, that your area vector is perpendicular to your magnetic field at all times, right? Remember, that's how we chose our intelligent Gaussian surface, right? So it's going to be the same thing here, okay? You can calculate magnetic flux when these two conditions are met. Okay, that's that. So again, coming back to Faraday's law, it's that the induced EMF, so in this case they call it E, we're going to call it E induced, or that, E induced. We're going to call that E induced. And E induced is going to be the change, or the rate of change of flux as a function of time. So we actually use differential equation notation, which is the small d's. And so I'm saying that basically the derivative of the magnetic flux is going as a function of time is going to be equal to that electromotive force that you're producing, that voltage that you're producing. Okay? That's Faraday's law. The direction of that voltage, though, we're going to be using Lenz's law to determine, and I'm going to talk to you guys about that later, closer to the end of today. So again, main topic for today is that the change of magnetic flux is going to induce some kind of voltage difference. Okay? So, okay, this is a complicated contraption. I'm going to have to explain it a little bit. I'll wait until you're done talking, until you're done writing, so that I can explain it. This also explains that problem in that last Hall effect PowerPoint that I skipped over, because we're going to derive the equation used to solve that problem as well. So after you've done this, you can go back and look at the other problem. Okay, so here I have some kind of trombone looking device, right? So right here, I'll wait a little bit. Okay, so imagine this here is a conductive wire, right? No current in it whatsoever, right? It's just a flat conductive wire. There is no voltage. It's not connected to a battery. You can consider it to be just a loop of conductive material. That's it. And here is a conductive rod. Also nothing attached to it, no current, nothing. it is a sliding mechanism on this part of the loop. So imagine it's like a trombone where you can like hold this part and then fling this part back and forth. Can you guys imagine it? Right. So that's what happens. I can do this and it's all good. Now, if I leave this stationary like this, I'm not moving this bar, right? What's happening is there a flux going into the loop created by this conductive bar and this part of that conductive wire? Is there flux? Yeah, because there is an area. I'm creating an area here, and there's a magnetic field, and the magnetic field is entering that area. In fact, it's entering it such that the area vector and the magnetic field vector are parallel. So you have actually a huge amount of flux. But do you have a change in flux? No, the flux is not changing. And if I don't have a changing flux, then Faraday's law is not working right now, right? So it really is, I can only induce a voltage, an EMF, an electromotive force, if I have a change in flux. So what I'm going to do is, I'm going to, at some velocity, change this and bring it really close, like the trombone, like I said it was. So let's say I bring it really, really close. As I'm moving, am I changing the flux? Yes, because what? Yes, the area becomes smaller. And as you know, the flux is the magnetic field times the area. If the area is becoming smaller, then the flux is becoming smaller or bigger? Smaller, exactly. All right, so now what's going to happen is, as I'm closing this, and because this is a conductive material, and again, there is no battery attached here, right? This is happening spontaneously. As I'm closing this, a current is going to start flowing through that part of the closed loop. So you've induced a current, you've induced a voltage that's driving that current. And if this wire had a resistor, so a load, then you're doing some kind of work as well. And that's amazing. The fact that all you're doing is you're moving something, a rod, in a magnetic field, and you're producing a current. Amazing stuff. Now, let me ask you a different question. Yeah. Difference in potential energy? Because remember Faraday's law is that if there is a change of flux as a function of time, right, then you have an EMF, an electromotive force or a voltage or something. And that voltage is what's going to be driving the current here. There's no physical battery and that current doesn't start or end anywhere, right? But the point is that there's a current. Okay? Now, does the speed at which I move this back and forth, or just back if you want to just consider one direction, if I go really slow or really fast, does that change anything? What way? Exactly. So again, the voltage that I'm producing, the induced voltage, is proportional to the change, the rate of change. So if the rate of change is huge, then the EMF produces huge. So if I were to do this really fast, then I would produce a stronger current than if I were to just slowly slide this over. Okay? Are you guys able to follow what I'm trying to say here? All right, so let's just derive something real quick. So I have that, I'm going to draw it here on the side. Am I in yellow here? Yeah, okay, good. I have my little wire here that has a length L at this part. I'm going to redraw this because it's kind of ugly. And L is this measurement here. And I have my rod here that I'm moving back and forth. Okay, I'm going to put an arrow to designate that I'm moving it. Okay. And this here is, I'm going to call this dimension S, the length, the position at which my rod is. I call that S. And I know that the formula for magnetic flux is equal to B times A, or B dot product A. It's all going to be perpendicular to each other at all points, at all times. And so therefore I can remove my vector notation, I can remove my dot product and replace this with just B times A. And my area is changing, right? Is my magnetic field changing? I kept my magnetic field constant, so my magnetic field is not changing, but my area is changing, and my area is multiplication. I mean, there's a square, there's a rectangle here, and it's a product of which two dimensions? Yeah, exactly. So my flux is kind of going to be equal to L times S, right? So base times height, if you want to think of it that way. And if I'm saying that the EMF induced, or the E induced, is equal to the change of my magnetic flux as a function of time, then I can write that it's the change as a function of time of everything that I wrote over here, B times L times S. Which of these three variables, B, L, and S, are constant? B and L are constants, all right? So now I can rewrite that my E induced is equal to B times L times ds by dt. All right. Now, what can you tell me about ds by dt? What is that expression? The change of position is a function of time. Yeah, and we call that speed, right? It's the change of distance, the change of position is a function of time, the speed. Oh, what happened here? Oh, get away. Oh, okay, hold on a second. Shoot. Okay, that's fine. Partager mon écran. Okay. So E induced now, I gotta go back to yellow. So E induced is gonna be equal to the magnetic field times the length of my my wire multiplied by the velocity. Oh, you don't see it. Mm-hmm. 9035. Yes. I just replace this expression, this ds by dt, I replace that by velocity. So if I just go back real quick, and I look at this, then I can measure the voltage produced here for this wire by calculating the velocity of this and using the magnetic field of my of the magnetic field that's being projected through this current. And if I have a resistor and I have that EMF induced, then I can find the current as well, right? And that would be the induced current. It would be the EMF divided, Ohm's law now, so EMF divided by resistance gives you current, or voltage divided by distance gives you current. Okay? And so here's that equation that we just derived, or it's just rewritten differently. It's VBL instead of VL. So far, so good? All right. We're going to need Lenz's law now. So we're going to come back to this. once we talk about Lenz's law. Essentially, the question becomes, now that we know that we're inducing an EMF, right? How do we know which direction the current's going? It's a loop, there is no battery, there's no positive terminal, there's no negative terminal. So how do we know which direction the current is going? Is it going clockwise, counterclockwise, upwards, downwards? I don't know. And that's where Lenz's law comes into play. Before we do that, I want you guys to practice how to just apply this. And it's asking you about the voltage induced or the EMF induced. And I just want to remind you that the EMF induced is equal to d phi by dt, and that and phi is equal to b dot a. So you'll need to know those two equations for this. Is the area changing in this problem? No, it's not. Is my magnetic field changing in this question? Yes. So if either one of them are changing, then that means my flux is changing. And if my flux is changing, that means I absolutely do have an EMF produced. Okay. How do you determine the area of a triangle? What's the formula for it? I didn't hear. Base times height divided by 2. And in this case, your base and your height is the same, so that's why I just squared it. Make sure everything's in meters, everything's in seconds. Did you guys get 0 or 4.0 times 10 to the negative 3? And it's asking you about the EMF produced, so I need to divide that by time. What did you guys get? Yeah, exactly. 0.08 volts, so the answer would be A. Any questions on this? All right, now let's figure out some little tricky situations. I'm asking you to rank these in order of flux. All right, so we don't know if there's a change in flux. We actually don't even care. All right, what we want to know is at this moment, what is the flux, or rank these in order of least to most flux. Nothing is given units, but you can imagine that they're all in the same units, so you can compare them easily. So I have to just remind you that flux is the product of magnetic field and area. And it shows you a little bit about the area here by telling you the dimensions and the strength of the magnetic field inside each of these areas. Therefore, how did you guys do the last one? Take a guess. If you don't know, it doesn't really matter. At this point, no one's giving you an answer, so might as well guess. It's the same as loop 2 and 3? Just loop 2? In what sense is it the same? You cut it in half, right? So do you say that the magnetic field is only applicable here? Is there going to be a current if this thing moves? Is there going to be a current in the whole thing? Well, I don't know about that. We don't even care. But essentially, you could consider it that there is only a flux string here, so you can calculate only the area of that. You can calculate the average area of the entire thing, the average magnetic field. So the average magnetic field for the whole area is what? 1. Or you can do what Kevin said, which is you take the magnetic field of just half. All right, so let's do what Kevin said. I'll find that one more intuitive. So the magnetic field is 2, and the area is 1 by 1, because the other 1 by 1 here is not does not have any magnetic field in it. There you go. All right. So in this case, if this were A, B, C, and D, A would be higher than B equal to C equal to D. Okay, here's where things get a bit complicated now. So I have a magnetic field, and this magnetic field is being shot into a circular area. Okay? If a magnetic field is being shot into a circular area, am I automatically going to get an EMF? No. What condition needs to be met in order for me to get a current in my loop? A change, exactly. So we need to figure out what the change of my magnetic field is, all right? So here I'm showing you what my magnetic field is as a function of time. But that I don't care about what the magnetic field is. I care about what the change in magnetic field is. So how do I find the change in magnetic field? Yeah? But it's telling you at 6 seconds. It doesn't say between 0 and 6 seconds, or the average change between 0 and 6 seconds. Yeah? Exactly. So I need to find the derivative of this function and evaluate it at time is equal to 6 seconds. All right. Let's do some derivatives. So I need to figure out dB of dt. In other words, I need to find b prime of t. And so how do I differentiate this? What rule do I use? Don't tell me the answer. Tell me the rule I need to use. Exponential rule? Not so much. You can use two concepts here. Which one? ln? No, we're not solving it algebraically. We're trying to find the derivative. You guys remember something called the chain rule? You guys remember the substitution rule? Substitution? Both of these will work in this case. All right. Let's do the substitution rule and let's get you guys practicing the derivatives. Yeah, right? Great. Yeah. Yep. Okay. So the derivative, the substitution rule is let u equal to negative 2t. Okay, so we're doing the substitution rule. And if we let u is equal to negative 2 times t, then we can say that du is equal to negative 2 dt. All right, so what I did is the derivative of u is du, and the derivative of negative 2t is negative 2 dt. So now I can replace that in my equation just real quick. Dt is going to be equal to negative du over 2. Oh, not negative 2, but 2. That's equal to dt. I just reorganized it. I just rearranged this equation here. I rearranged it into this, because that way I can plug it into my equation. And I can say that 10 e to the negative u is going to be equal to my dB over dt, but now my dt has changed, so I can bring the 2 over upwards. Ugh. Ugh. Come on. dB is going to be equal to times negative du over 2. Is that correct? How about you? Oh, wait. So, you have to take off my e. There. All right. So then my change in magnetic field is now going to be 5, or negative 5, e to the u du. Oh, goodness, so buggy. Du. Yeah. How did I get from here to here? It's the derivative. So the derivative of u is du, and the derivative of negative 2 dt is negative 2 dt. Negative 2t is negative 2 dt. I feel like I'm doing this wrong though. It should be minus 20, the answer, not minus 5. It's not divided by 2, it should be multiplied by 2. But why though? Where's the mistake? It's just not divided by 2, but what do you mean? Here, you mean? Here? Come up and show me, because I'm confused now. I haven't done derivatives in a while.
This is the derivative for exponential, where it's well the exponential part stays.
Yeah,
This stays because it's a constant.
yeah,
And then you do times
right.
ln of the base times derivative of
The
the u,
inside. Okay.
and it's just the derivative of u, so derivative of u equals the minus.
Oh, I see. Got it. Okay. I'm starting over, guys. Let's go back and let's not use substitution. We'll use the chain rule. And the chain rule is you take the original function multiplied by the derivative of the inside. So that would be 10 e to the minus 2t multiplied by the, oh my god, it's so buggy. So b prime of t. So it's going to be the original function multiplied by the function inside the function, in which case is a derivative of negative 2t, and the derivative of negative 2t is negative 2. So you multiply this by negative 2, which gives me negative 20 e to the power of negative 2t. That would be your, yeah. No, you can use it for derivative. Yeah. I did this yesterday using substitution, and I thought we would do that one because it's the harder one, but I don't remember it. Okay, we have our function now for the change of magnetic field as a function of time. We need to know what that change is at time is equal to 6 seconds. So we actually need b prime of 6. So if we need b prime of 6, I'm just going to go do that down here. It's going to be negative 20 times e to the power of negative 12. Can someone do that? It's going to be a weirdly small number. Minus 1.2 times 10 to the minus 4? You sure? It should be a much smaller number. Did you get the same thing? 10 times the negative 4? I don't believe you. Because how could something times 10 to the power of negative 12 give you such a small number? Give you such a big number? Oh, you guess you're right. Okay. What are the units of this? It's magnetic field, or the rate of change of magnetic field, so that would be Tesla per second, exactly. Yeah. All right, so that's my change in magnetic field. And if I find my change in magnetic field, I can find everything else. So it's going to be the delta B, we're going to call it, multiplied by the area. And the area, well, we know that because it's got a radius of 1. Yeah. Radius of 1 centimeter. So that's going to be, what's the area of a circle again? Is what? Pi r squared. Pi r squared. Don't forget to keep that in meters. This is why I thought it was going to be a small number, because I had done this yesterday with this value. So what'd you get for the area multiplied by the magnetic field? You should have a really small number now. You guys need paper towels? Should be some here. Watch out for your electric stuff. Okay, what did you guys get for area? I can't hear anyone. Minus 3.8 times 10 to the minus 8. Now hold on here. So I have to figure out units here because otherwise I'm going to go nuts. Is this in fact this the change of magnetic field, or is this the change of magnetic field as a function of time? The value that you used here, if you plug this in here, it was delta B over delta T actually. So now if I have that, this is all equal to my E induced. And if my E induced is this, my units are going to be volts, right? Because I'm literally producing a voltage. And finally, last step is it's asking you for the current. So if I have a voltage and I have a resistance, the resistance is given here as 0.10 ohms, then you have to find the current. And that's easy. It's just Ohm's law. V over R is equal to I. V over R is equal to I. So that means it's going to be negative 3.8 times 10 to the minus 8 volts over 0.10 ohms. And that's going to give you negative 3.8 times 10 to the minus 7 amps. And this is your final answer. The resistance is 0.10 ohms. Yeah. We'll explain that with Lenz's law. Okay, so for all intents and purposes, you can ignore the negative sign for the current and for the voltage. Lenz's law is going to allow us to determine the direction of that current. So ignore it. If you want, just erase it. Okay? So here he is. Basically, what Lenz is going to talk about is when you induce a current, you're going to induce it in such a way that the induced current is going to oppose the change of the magnetic field. Okay? It's complicated. We're going to, I want to show you guys a couple videos. Is that what it is? I want to show you guys a couple videos, and then we're going to practice using Lenz's law. I hope the sound works. Otherwise, this is going to be super lame. Again. It's just what you need to know from the beginning is that there are two tubes. One of them is made of aluminum, and the other one's made of glass. Two magnets that he's going to drop in those tubes. Is aluminum magnetic? No, it's not. All right. So it's not because of the attraction between the two poles of the bar magnets. and the aluminum that you're going to see, that you're going to notice this phenomenon. So again, he's going to drop them in at the same time, and at the bottom you can see what's going to happen, which one gets to the bottom first. Okay, so let's see if we have a better view of this. I'm hoping I could make
Magnetic braking is a type of braking which doesn't rely on mechanical pressure, as is common in most braking systems.
You'll have to listen to it through my speakers, and it's going to be ugly.
Deceleration. Using the following cartoons, we can explain the processes that are actually happening. Again, we see the magnet dropping through the tube. The red line. This variation in the magnetic field induces an electric current, as predicted by Faraday's law. Doesn't rely on.
It's super lucky. I think there's a room downstairs, and I think would be. Let's go downstairs in room 2 floors down, room 306, I believe. This is gonna be fun. All right. Let's see if there's everyone here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yeah. Okay. Let's see how this works.
Magnetic braking is a type of braking which doesn't rely on mechanical pressure, as is common in most braking systems. We'll demonstrate this type of braking using
Not my that. Okay. I think it's just a loose connection.
a magnet and a copper tube. Unlike iron, copper is not a magnetic material, so the magnet won't physically stick to it. Therefore, a magnetic attraction cannot be the reason for any slowing in the fall of the magnet. A slit has been cut in the front of the copper tube so you can see the magnet as it drops. As you can see, the magnet falls much slower than you might expect.
Let me call JP. Take a 5-minute break. What's his number? That's 652 for JP. You guys know? No. So, how can we get this to work? Have an idea? There's one out in the hallway. It's not so much the lag, but it's actually just cutting in and out. I think the wire is loose somewhere.
We can drop a non-magnetic
I have a pipe.
Yeah.
Do you want to hold it? Do you know what it's made of?
Metal? Is it brass?
Copper.
Is copper magnetic?
No.
Uh-oh.
I'm gonna go no, I didn't think it was.
Can't do anything. Are you guys able to connect to my Adobe Connect? Can you guys connect to the Adobe Connect? You guys remember the channel? You guys is NYB01. Go, connect. I just want to know if there's like a frame drop, any frames dropped. So when I'm playing the video, see if it's smooth and whatnot.
I have a pipe.
Yeah.
Do you want to hold it? Do you know what it's made of?
Metal? Is it brass?
Copper.
Is copper.
Okay, what's going on? So is it? It's super laggy. All right, well then screw this. It sucks because the videos are actually really cool. What would be a better solution? Let's watch just one of the videos, and you guys, you don't need sound for this. So you guys just mute it on your computer so that you're not like distracting everyone else. I'll send you the, tell you the link for it. The video is called, oh, it's in Russian. Good grief. I'll email it to you. Okay, here we go. Last ditch resort. Go here. All right, I'm going to email you a YouTube video. Just watch it. Okay, please go to the video I just sent and watch it. And our bigger issue is I have no projectors. So now we might actually have to go back upstairs if you're really super lame. How is it that I need this gigantic box to make things work? It was in and out. It wasn't really working. I'm not going to touch it anymore. Okay. You guys get a chance to see it? Yeah, everyone? Okay, so what that is something called magnetic braking. I had a whole video on that. It's going to be super cool. But the links are there anyway in the PowerPoint, so you guys can go and check them out. And you can listen to it because they do explain it a little bit. There is one thing that I really wanted to show you at the end of today. Hopefully, I can get it to work even for like 20 seconds. I can that one part. But essentially, that's what lenses are, right? So now, what you notice is that when you drop the magnet in this copper tube, or when you were spinning that really cool magnet inside of that big copper tube, that it slowed down. That gravity wasn't necessarily working as much as it normally does. It wasn't accelerating. That means there was a force in which direction? In the upwards direction. Okay, exactly. So if there's a force in the upwards direction, that's what we got to go by. Okay, and so Lenz's law applies. The gist of things is that nature is lazy, right? Whatever you do, nature is going to resist as much as possible. All right, you're going to try to drop something. If you want to, it's going to resist the motion. So it's going to be all sorts of forces acting on it to resist it, but essentially, there's going to be one that's going to win. But nature is always going to resist it. So let's go to what's happening in this loop here. Okay, if I have a magnet and I'm moving it downward, this first of all, this magnet has some permanent electric field lines, right? So if I were to, I'm afraid of moving this because it's so sensitive. If I were to draw this magnet, it would have magnetic field lines in the wrong direction, and of course glitching would be in the inwards direction, because remember, magnetic field lines are always towards the South Pole. All right. At this position, I only drew 4 lines, and we're going to assume that there are only 4 lines. So at this position, 2 of those lines are going through this loop. So there is in this loop there is a certain amount of flux. If I bring this closer, what's going to happen to these lines? Are they also going to go in the loop? Yeah. So is the flux going to increase or decrease? The flux is going to increase, all right, and it's going to increase in which direction? The magnetic field lines are going upwards, so it's going to increase in the upwards direction. Right, so I bring this down, and there's going to be an increase in magnetic field lines upwards. The flux, the change of flux is upwards. So what nature is going to do, and this is what inertia is it's going to try to oppose that. It's going to try to oppose that magnetic field by inducing a current in the loop such that the magnetic field produced opposes the change. So you guys said it increases upwards. So what's going to happen is there's going to be a induced magnetic field downwards. Okay? And if you want a magnetic field downwards, how do you produce a magnetic field downwards? Well, now you have to use your right hand rule. You put your thumb downwards and you wrap it around. You know that the current induced is going to be in this direction. Okay? So you're inducing a current in the loop just by changing its magnetic field. So then now we know how to do its direction as well. Before we figured out that the change in flux is going to induce a magnetic field, electromotive force, and now you know the direction of that current produced based on this principle of law. All right, and don't worry if this first example has you confused. We're going to do like 10 of these, and I'm going to drill it into you until everyone figures it out. I want you guys to do this one. It's the same problem, except this time the magnet is moved upward. Okay? So what I like to do, I'm not going to have room to, I don't want to touch this too much because it's so sensitive. I'm going to draw what I call a situation initial. Here's your situation initial. You're moving upwards, so you're starting off closely. And this is your situation now. And your loop is now further away. All right. Over here, let's say there were 4 field lines. And over here, there's still 4 field lines. But now these ones, they don't necessarily go into the loop. But these two middle ones, they do. So what happened to the flux? The flux decreases. The flux decreased in which direction? Upward direction. Okay, so it's going to, now nature is going to oppose that, and it's going to induce a magnetic field in which direction? So it decreased in the upwards direction. It doesn't want it to decrease, so it's going to induce a magnetic field to oppose that decrease. So which direction is that magnetic field going to be induced? Up. It would be up, right? Because now there was now there is so nature. Okay, so there's going to be an induced magnetic field in the upward, and we're going to call this B induced. And B induced is going to be caused by a current. We have to use our right hand to figure out which direction that current is. So which direction is it? What is it called? Counterclockwise. Okay, that's going to be your induced current, the direction of your induced current. Yes. Okay, so let me restart. And it's normal. All right. So your question is the magnet is moved upwards at a constant velocity. So this is moved upwards. So first it's close to it, and then it's far away from it. Okay, and a magnet is always going to have magnetic field. I only drew four because I don't need to draw more, but there are many. All right. So therefore, when I'm close to it, all four pass through the ring, correct? But when I'm far away, because they kind of like deviate away, they turn outwards, they're too far now to go into the ring, right? So there's four arrows going upwards here. That's initially. And then after, there's two arrows going upwards here. So it's less up than it was before. Okay, there's less up arrows. So what nature is going to do is it's going to produce its own up arrows to compensate for those decrease of up arrows. So it's going to be a B, we're going to call this B induced, magnetic field induced is going to be upward. But a magnetic field doesn't come out of nowhere, right? You can't just have a magnetic field all of a sudden. You need to have a current in order to create a magnetic field. And we learned that using our right hand, right, that a current is going to produce a magnetic field. And a magnetic field is in the direction of our thumb. And with our finger, we can find out the direction in which it goes through the loop. Yes, Elizabeth.
So when you compare how many or how the magnetic field is, you have to compare it to the original.
Yeah, exactly. Because remember, it's a truly magnetic field. If I just showed you this picture, you wouldn't be able to do anything.
Yeah.
Okay? We're going to do this again and again and again until you figure it out. All right, do it this one now. It's the same thing. This time you're moving with the north and you're moving down. You don't need to whisper. I want you guys to talk it out. I encourage you guys talking it. Yeah.
And the ring is conductive.
Yeah. If it was not conductive, then you could assume that there would be no induced current. Who has an answer for me? An explanation. Yeah, okay. Hey? And explanation.
Magnetic field going down
Okay.
because as it goes down, more lines are going to
Okay.
flux is increasing on it. And so it'll want to counter that, so the induced will go up and the current will
Very good. So as you drop this magnet into the ring, you're making the arrows more down, right? And nature is going to oppose the more down by doing more up. And more up means put your thumb upwards, wrap your fingers around in the other direction. Okay? Exactly, exactly. The magnetic field will produce a force on. This has something to do with something called eddy currents, and I would have explained that if the videos were. But essentially, there's from the magnetic field, there's going to be a magnetic force pushing upward. Okay, next example. Ignore this drawing here on the left. Just go for this one, okay? Now it's a solenoid, so you're going to have to use a solenoid right hand. Yeah, what's the direction of the Which way is the bar magnet's electric field pointing towards? Left or right? Or up or down? Left. Right? Are you pointing left or are you pointing right? So if I have a magnet, the magnetic field lines are pointing in which direction? Away from it, right? Because it's coming out of the north. All right, so I have magnetic field lines coming out of my my magnet. Try one more. All right, perfect. And as I get closer, if I bring this magnet closer and closer into the solenoid, is there going to be more magnetic field going towards the left or less magnetic field going towards the left? More. So the induced is going to be in which direction? To the right, exactly. So my magnetic field induced is going to be towards the right. When it's humid, this thing gets so buggy. Okay, so my B induced is going towards the right. That means I can use my right hand rule and figure out what direction my current is. So in the back, it's going to be upward, and the front is going to be downward. So my B induced is going to be like this. And if my current is coming down, so I can actually follow it, the current's actually going into my negative, right? So I'm going to draw my arrow like this, going into my negative. You can barely see that. And if my current is going into my negative, then my ammeter is going to go point towards the negative end. So I'm going to have an arrow here, and this arrow is going to, oh my goodness. My arrow is going to be pointing towards the left. Is this starting to become more clear? Yeah. Okay, last example, and I'll show you a 20-second video and we'll call it a day. So again, what I want to emphasize is I want you to draw what it looks like in situation initial. So situation initial is that the loop is over here. Situation, I guess secondaire, it's not final yet. It's over there. Oops, too big. And this is what it looks like after. So my loop, and my loop is at the top of the magnet, and my loop is at the right. All right, and this magnet's not moving, and there's nothing changing about my magnet, so my magnetic field lines are always going to remain the same. All right, I'm always just going to draw 3 in this situation. In the question, it says a counterclockwise current viewed from above is considered to be is considered to be positive, and clockwise is going to be considered to be negative. Right? Just so that we're not. So, it is magnetic field as this increasing, increasing in which direction? Upwards, all right? So that means that my induced is going to be, say it louder, downward, yeah, it's still not loud. I heard you now, but now it's still not loud. So I'm going to induce it downwards. So I have a B induced downwards. And if I were to use my right hand, if I'm doing a B induced downwards, then it's going to be going in this direction. And as viewed from the top, is that clockwise or counterclockwise? Clockwise, and clockwise according to this automatically, I know that A and C are not the right answers. Because it starts off with a negative current. All right, once it's here, and now it's moving away, is my loop's magnetic flux increasing or decreasing? Decreasing. And is it decreasing in the up direction or in the down direction? In the up direction. Okay, because the magnetic still pointing upwards. It's just less up now. So if it's less up now, how is nature going to respond? By inducing magnetic field in which direction? More up, exactly. B induced is going to be up. So here we go. B induced is going to be up. And if my B induced is up, back around, now I'm going in the other direction. And that's counterclockwise, which means that it's positive. So it was positive at a certain point. So my answer could therefore only be D. Elizabeth, you had a question? You understand? That makes sense? So far, medium? Okay, we can do one more example. Let's do one more example. All right. In each of these situations, let's state whether they are true or false. So again, I have a magnet going inwards, all right? My magnetic field is pointing up or down, first of all, for my magnet. Magnetic field is pointing down, all right? As I get closer, how much arrows are going into my arrow? More down or less down? More down, all right? So that means that nature's going to oppose the fact that there is more downward arrows by creating an upward magnetic field. An upward magnetic field would mean that my current is going in this direction, all right? And this is correct here, right? It'd be going, wrapping around like that. So this one is correct. This one I would say is true. Okay. Now I have this opposite situation from this, right? I have a magnetic field pointing downward. As this gets further and further away, there's going to be more down or less down arrows. Less down arrows. So nature is going to oppose the fact that there are less down arrows by producing more down arrows, right? So that means my induced magnetic field is going to be downward. All right, now you're going using your fingers again, you're going to go clockwise, right? And then for the current is correct again, it's going to wrap around and go in this direction. Okay? All right, so this one's also true. Now this one, you have a south pole now going this way, and the south pole has magnetic field lines going upward. All right, so that means is there going to be more up arrows or less up arrows? More up arrows, nature is going to respond by adding its own up or down. Down arrows. So I have a down arrows, I put my thumb downwards, wrap my finger around, and that's in the correct direction again. All right? Now you guys do this one, tell me if it's correct. True, exactly. It's going to be less up, so it's going to respond by going down. And if I put my hand, is it all right? Oh, it's going to be less up, so it's going to respond by going upwards, and then my fingers are going to wrap around, and it's going around in that direction again. Okay. All right, that's my last example. I do have one video I wanted to show you guys. I'm not sure I'm going to be able to, so please bear with me. Okay, that's not the video I want to show you. Ah, come on. It was working this whole time. I have no idea. I have no words. I'm going to bring it up.
I have my spin that magnet. That needle. How much current I'm actually moving.
Okay, I'm just going to go ahead and play it. I'll pray to the gods of Windows 10. Sorry. All right, let's see if this can work for 20 seconds, please.
Moving inside the wire itself. Why is that? Now the magnetic field lines, you can see the magnetic field lines are changing, and as they change, we're getting change in magnetic flux, and so we're getting current inside the wire. Now another way to look at this would be through a generator, and so in this setup what I have is a magnet down here on a wheel so that I can spin that magnet.
What I want you guys to pay attention to is actually what's happening. Right? What's happening with the current and what's happening with the magnet and all that stuff. But really importantly, what's happening with the current. These dots, these blue dots represent charges in a wire.
I have my wire again, and I'm trying to induce current inside that wire, and then I'm going to measure the amount that I'm going to change. And so watch what happens now when I start to turn on the water inside that faucet, it's changing the position of the magnet. As it changes the position of the magnet, it changes the magnetic field. You can see the magnetic field lines are changing, and so I'm starting to get a little bit of current. What happens if I increase the speed of that water? I'm getting more current. We could even have a light bulb connected to it, and so now I'm starting to get usable energy. Watch what happens as I increase the number of wires. I even have more energy coming out. And now if I increase the water again, I even have more energy being produced. And so we're taking that energy of the flow of the water and actually making electromagnetic energy out of it. And so this is how the generators in a dam would work. We have the water flowing down through the dam. It's spinning these magnets, and it's creating that electricity. And so did you...
All right, so real quick before I let you guys go, really what I wanted you guys to get an understanding of is we use this exact principle in Hydro-Quebec dams. And what they do is, or hydroelectric dams, not just Hydro-Quebec ones, but hydroelectric dams, they work all with this principle. Water is turning a magnet in a turbine, and that turbine is changing its magnetic field inside a coil, and that coil is actually directly connected to the entire country, all right, in terms of Hydro-Quebec. I mean, we have Hydro-Quebec lines that run all the way up into the western provinces. So really, and we actually even export some to the States. Although now I'm not so sure anymore. I think there might have been some changes in the agreement. But the point is that that's how. And the second important thing is, did you guys notice that when he was turning it, what did you notice about the blue dot? They're going up and down. Up and down. If it was a DC current, they would all be going. But this is generating an AC current. All right, that's how you get this sinusoidal voltage, is because we have a magnet producing current in both directions. So rather than wasting half of that energy and only feeding the positive direction currents to the entire grid, to everything that needs power, what we're doing is, well, why not just use both? And what we have in all our devices basically is these diode rectifiers, and they're converting these currents so that we're not wasting any type of energy. Isn't that cool? I think it's cool. Sorry about all the technical issues today. It took a little bit longer than I expected, but such is life. Next class, I'm going to continue with this, right? It's just going to be more examples with derivatives and all that stuff. So if you think you need a refresher, please bring your notes or do something about it, because the derivatives are going to be hardcore next time. Have a great day. What's your question? Does it work? Oh, what are we're talking about it. Oh, okay. So then, I'm not gonna just start giving willy-nilly one. But like there are some people there will be a few people. I'll talk to him and say, see what it's. I think he's trying to solve the problem. Solve the problem? Solve the problem. As of now, it's not. When did it break? I think after the. So does this work? I'm gonna make it prettier and more like. Oh, that's like a mole, right? And I'm gonna bring it over. programming, you have to do that.
Yes, I mean, there's a code online, and I'll have to modify.
I did a program for programming. It took me more time than I did this. And my dad done more over this than over my program. It's very confusing.
You help you with this?
No.
How do you start?
Oh, because this is a free game.
Okay.
So.
I got that wrong.
No, every time it's randomized.
Okay, so I just start with this.
You go whatever. There's a pre-game round, there's and then there's a long.
Time do I have?
You don't, it waits
Wait forever.
for your input. Yeah, because if I put in a number of times, it will come back. Yeah. I took inspiration from two different places and I just it in my own.
What?
Yeah.
Right. Oh, it goes up to 5.
Yeah. You have a better, because it's pretty far. Now, there's a Are you gonna close it a little? I want to, though. Arduino has a library of songs. Arduino has a library of songs.
All right.
This one that's gonna make the songs on morning wake up song. It's like the windows of like the Mac. Yeah.